Right. Good morning, everyone. And I'd like to thank Cindy for inviting me to present at this very important North Coast IPM seminar. Uh, I mean, by training, I'm a plant physiologist, so I work on the physiological aspects of this disease and how to translate these to cultural practices based on what we found so far since my arrival at the Oakville station. So grapevine red blotch is not new anymore. We do know some things about it. As we phenotypically see it, we see the red leaves on the grapevine. We end up with unripe clusters on the grapevine at our harvest. And what we usually end up with is reduced growth, sometimes reduced yield, but more often than not with lower quality. And we try to combine these things to come up with some mitigation methods to move on in our practices if we're going to keep these vineyards for a limited amount of time. So we end up with lower yields and quality and red leaves, but this starts with a virus infection. So with virus infection, we get the red leaves, higher acidity, we get the reduced growth, we have a some kind of a better water status in these plants with larger berries that end up somewhat unripe, with poor color and a high acidity, aroma and a flavor is affected in the end. To be able to elucidate these chain of events, we need to propose an alleviation or a management strategy for the long term. Although these vineyards are being removed, they're being removed at a smaller pace because pulling up vineyards and putting in new vineyards without an identified vector is kind of a no-win game at this point. So what we know about the red blotch infected grapevines is we have these paradoxical water relations in grapevine red blotch disease infected vines. These better water status was combined with a lower stomatal conductance. So our general assumption has been that we irrigate this much, and the plant will take up this much, or some of it will not be taken up. It'll roll off the vineyard floor, or it'll evaporate. Interesting to know that plants will close the stomata if they do not need the energy. So there has to be a sink demand or a photoassimilate demand from somewhere for the plant to use this water. So in red blotch infected plants, we have red leaves, right? So this suggests that photoassimilates are sequestered by the plant, but they're stuck in the leaves. So previously, we have proposed this whole plant mechanism, and this is how we continued working on our trials. Grapevine red blotch disease is impairing sugar transport in the grapevine. These carbohydrates that are made through photosynthesis are accumulated in the leaves. Stomata are closed. We have reduced transpiration by the grapevine. So we also have the accumulation of water not used in the soil, and we end up with a better water status. So that's the paradoxical water relations in red blotch infected grapevines. When we looked at this with two different rootstocks that had different hydric properties, we compared 110R and 420A. They use water quite differently. We have seen transient differences in red blotch infected plants. More importantly, in 428 that does not use water as effectively. So what we're seeing is that the plant is not photosynthesizing as much as it should, although it has plenty of water, because the berries or another sink is not calling for it as much as it should. So it's not necessarily a lack of a ripening signal. The photoassimilates are stuck somewhere in the plant. It's not going where it needs to be. But more often than not, as the years go by, this transient reduction in our photoassimilation is going to affect the plant. The grape ripening is the best way to assess this. There's an inherent relationship between ripening speed and photoassimilation, but what we're seeing is mild reductions in photoassimilation. What we're seeing is a huge reduction in sugar assimilation into the plant, or its translocation. So when we compare these red blotch negative, red blotch positive vines on the 20th of September, on a 110R, there's almost a 5 degrees Brix difference between red blotch positive and red blotch negative vines. Likewise, in the less vigorous rootstock 420A, we see the same response. We waited to harvest these, as you will see in the later slides, but this response is, very consistent over the years. There's this, reduction of ripening speed as the berry ripens. So it's not being translocated into the berry. Of course, we do grow grapevines for their phenolic properties. Our experiments are mechanistic in the sense that we have run these trials only with the presence of red blotch. We do not have any other co-infections. They either had a red blotch or they had no other diseases. They were clean. So when we compared the grape ripening, the color or total anthocyanins in milligrams per berry, this would be how much anthocyanin this plant made and transferred it into the berry in the end. We see a similar response to ripening speed till about 21 Brix. Okay, so in this case, when the grapevines do not have a red blotch infection indicated by RB negative in this case, they're ripening somewhat similarly with both rootstocks. However, as the berries start dehydrating, when there's no more biosynthesis of anthocyanins, you start seeing the red blotch negative vines also decline in anthocyanins. So there is no change close to harvest with color or anthocyanin content on a biosynthesis basis per plant. So why would anyone want to worry? Well, because when you compare samples picked on the same date, this does not explain the whole situation. This is just too naive to say that as like, oh, it's low. There's an inherent relationship between total soluble solids and anthocyanin production in the grape berry. So anthocyanin or anthocyanin biosynthesis is called by sugar stimulus. As long as there's sugar going into the plant, the berry will make anthocyanins. So in this case, we compared total soluble solids evolution to anthocyanin evolution in red blotch positive and red blotch negative vines. As you can see, red blotch positive vines indicated by the red line here, okay, the red regression line, they never reach a proper biosynthesis of sugar. Therefore, they're only going to make about 2 milligrams of anthocyanin max. This is per berry. Conversely, red blotch negative vines, they will make about 2.5 milligrams of anthocyanins at the same ripening speed. Okay, so there's more sugar there, and therefore there's more anthocyanin. So what if we were to compare these harvested on the same day and the column graph here on the other inset? So red blotch negative, red blotch positive, SD means same day, red blotch positive at same maturity. So we waited till they reached 25 bricks. Okay, we either harvested them on the same day when our red blotch negatives reached negative 20, when they reached 25 bricks, or 22 and a half bricks, or we waited till the red blotch positive vines reached 25 bricks, essentially dehydrated. Even if you wait for them to reach the same amount of bricks, they will not make the same amount of anthocyanins. So in fact, they will degrade. You're going to end up with less anthocyanins than you had at 22 and a half bricks. It doesn't matter what kind of rootstock you had. In our case, we had two very large extremes, 110R and 428. The response is the same. The titratable acidity of our red blotch positive grapes, it's consistently different if we look at it across the date, but if we plot it against maturity, there's not a whole lot of difference in the titratable acidity of these grapes. Bottom line in this case, red blotch disease does not affect titratable acidity directly. It will affect it indirectly as the berries dehydrate on the vine, and as these organic acids are respired. The pH of red blotch positive grapes, the red blotch positive with the same bricks, you're going to end up with a much higher pH, with much higher pH. So if I plotted across days, I can see some transient differences. If I plotted against maturity, as you can see, as I'm dehydrating these on the grapevine, if I pick them on the same day, not much difference. If I wait till the red blotch positive grapevines reach the same maturity in bricks, I end up with a much higher juice pH. It might be not as manageable as it previously was. So this is the plant berry response from a physiological point of view that cascaded through the photoassimilate calling by the sync response on the grapevine plant. So this is the chain of events that we have identified in this. The effects of grapevine red blotch disease in the short term, it's impairing sugar transport. As it's impairing sugar transport, carbohydrates are accumulated in the leaves, okay? And this immediately responds in stomatal closure. The sugar eliciting anthocyanin is what's causing the red leaves. And we do have the response from the berry that carbohydrates not being accumulated in the berries. The stomatal closures are resulting in a reduced transpiration by the plant, and this results in a transient reduction in carbon assimilation. There's a delayed ripening process through the course of titratable acidity respiration, and as well as proanthocyanidin or tannin degradation. We have an accumulation of water not used in the soil. So this results in a lower contribution of total soluble solids accumulation, which in turn results in a delayed harvest with higher pH but lower color. In the end, the plant has always a better water status. This is what results in larger berries, and this is what's resulting in a dilution of berry content with a lower total soluble solids. Long term, this is what we're working on now. Grapevine red blotch disease is impairing sugar transport. You have a late ripening. You have therefore a lower capacity to accumulate reserves. What I would term this as plant weakening, such as reduced root growth, which I'm not going to present today, as the studies are still going on. And we are also looking at a reduced bud fruitfulness and a rate of shoot growth as the years go by. This is how I had summarized it previously. Of course, we have the red vine, grapevine red blotch canopy with the positive leaves that accumulate anthocyanin for color accumulation. And I will make these slides available. This is the summary of what's upregulated and what's downregulated based on the plant primary metabolism and the secondary metabolites in the berry. Surprisingly to us, there was not a whole lot of difference in pro-anthocyanidins or their mean degree of polymerization in the skins, which a lot of tasters said they could taste this, but we could not measure this. As we moved on these trials, we were fortunate enough to garner a grant from USDA. So we're working on the mitigating the effects of disease in the field. So what we were assigned was to look at some of these cultural practices, such as the questions that we received from the grower panel. Does crop level affect this? Does applied water amounts affect this? There's a lot of interest in using foliar sprays. And then we constantly get questions about, can I apply a ripening agent such as a abscisic acid hormone to, make the grapes riper? All these experiments were done both at the university and grower locations. So I will show you a summary of the results we have so far. The experiments started in 2020, this year of the pandemic. All experiments are done on a Cabernet Sauvignon Clone 7 with rootstock 110R that was planted in 2012 on dormant bench grafts, and the grapevines came from a commercial nursery. All experiments are done on a same soil type, bale silt loam, and all the grapevines were trained to a vertically shoot position system. So everything is the same in all these trials. The crop level trial, we wanted to elucidate the response of the grapevine to a reduced crop level under red blotch positive and red blotch negative conditions. Since we were seeing a response from the grapevine for reducing carbohydrate translocation, the immediate response from growers is to like, well, I'll just keep less clusters on the grapevine to make them sugar up. So we set up this trial. Trial was arranged factorially. We had virus status, plus or minus, and crop level on a 6-foot spacing. We either kept 45 clusters or we either kept 15 clusters. We reduced the cropping level by 2/3 to get the response from the plant. And we did the physiological response from plant water status, gas exchange, components of yield, and fruit and berry metabolites to assess if this carbon translocation or sugar transport impairment can be overcome by reducing the crop level. Here's the gas exchange results. I'm showing you 2 time points at veraison and also at pre-harvest, right at 21 bricks. This is a table where I have a grapevine red blotch positive, grapevine red blotch negative, 1/3 of the crop, and full crop. They're reducing crop did not change the photosynthetic response at veraison or at pre-harvest. However, we have a response from stomatal conductance. The plant has to have a sink for the water to be called onto this, okay? And the response was paradoxical at veraison compared to pre-harvest. At veraison, when we had a higher full crop, okay, we had a less stomatal conductance, higher stomatal conductance in the 1/3 crop. Virus status did not affect the stomatal conductance. Pre-harvest at 21 bricks, we have a response of both virus status and cropping level. Grapevine red blotch positive vines had a higher stomatal conductance in this case, uh, as well as a full crop that had the a higher stomatal conductance. So in this case, the plant was trying to make up for lost carbohydrate translocation by trying to use more water. But however, let's see if it had a response. Well, of course, cluster number is not going to change by a virus status. They're essentially the same. Cluster numbers are going to be reduced by the cluster thing that we apply. Crop weight is different. However, we're not seeing a difference in cluster mass or berry mass in this case, which can be interpreted as a positive benefit, because usually we see a higher or larger berry size that might dilute the total soluble solids with a red blotch positive response, but we did not have a significant difference in this case. When we look at the primary metabolites at harvest on the same day, of course, virus status has a huge impact on our total soluble solids accumulation. Again, we see the 4 degrees Brix or total soluble solids difference. Reducing the crop did not affect anything, and we do not have an interaction of cropping or red blotch virus status. Likewise, we do not have an interaction of cropping and red blotch status. Likewise, in titratable acidity. The main effect that we get in pH in this case was with cropping. Full crop had a higher juice pH. Crop leveling perspective, removing 2/3 of the clusters, of course, results in a yield reduction. You have a transient response to a gas exchange that did not alleviate the or palliate the virus presence. There is no response to carbon allocation as seen by the lack of response to total soluble solids. And then it does not palliate this lack of carbon translocation, and it's not necessary to conduct this in a red blotch positive vineyard. So there's no reason to drop these clusters if you have a red blotch infected grapevines. The applied water mouse trial, we wanted to elucidate the response of a grapevine to applied water under positive and negative conditions. Again, we had a factorial arrangement of treatments. We had a red blotch positive, red blotch negative vines, and we applied water at a 50% of crop evapotranspiration demand versus 25% of crop evapotranspiration demand. Again, we had documented the plant water status, gas exchange, comparison of yield components, and primary berry metabolites. So here is the gas exchange results. We at Verazon, and again at like pre-harvest at 21 degrees Brix, photosynthesis in grapevine red blotch negative vines, pre-Verazon is higher. Stomatal conductance is also higher. When we look at the irrigation, at a half irrigation, we have a higher photosynthetic response, but a higher stomatal conductance at a full irrigation. So we interpreted this as if we applied it at a half irrigation, there was lack of carbohydrate. The plants were carbon starved in this case. It was calling for more photosynthesis or assimilates. However, we did not have an interaction at Verazon. Conversely, pre-harvest, as we applied more water, we were able to see an interactive response of grapevine red blotch positive vines to a full irrigation that was similar to a red blotch negative response. Likewise, we saw the same thing in stomatal conductance. So replacing 50% of crop demand in this case was helpful rather than reducing the applied water. or imposing deficits. Not a whole lot to write about in components of yield in this case. Crop weight was essentially the same, cluster weight was essentially the same, and berry weight was essentially the same. In this case, our results were encouraging to see that we did not see larger berries by doubling the total amount of water as a response to diluting the TSS even further. We got even more encouraged with the primary metabolites at harvest. As you can see in this case, we're getting a good response from total soluble solids, both at half and full irrigation with positive and negative red blotch red vines. Likewise in pH, likewise in titratable acidity. So we're able to coalesce the differences between red blotch positive and red blotch negative vines by irrigating them a little bit more. So our recommendation in this case, and this was published by my colleague at Oregon State University, Alec Levin, we are recommending that you do not reduce the applied water amount to red blotch positive vines because you have better photoassimilate production by the red blotch positive plants in this case. We do not have a change in yield. We do not have a change in cluster mass. We do not have a change in berry mass. And we end up with no detrimental effects on the sugar allocation in this case. It is strongly recommended not to apply deficits to grapevine red blotch disease grapevines. Then we looked at the homologues of abscisic acid. The commercial product is called Proton. It's labeled to be applied in grapevines. I cannot see my chat. I don't know what it says. It's gone away. We want to illustrate to a response of a ripening enhancer under these conditions. Again, same setup, virus status plus minus, application, 300 parts per million of ABA versus 0 parts per million APA. So we had no effect on our leaf gas exchange, no effect on our plant water status. We had a very slight increase in our bricks, not significantly different. Slight increase in our total skin anthocyanins, not significantly different to our abscisic acid application. So our perspective on our cultural practices, these studies will go on in a larger scale. The impediment on our carbon translocation GRBV positive plant is difficult to overcome. Removing our clusters do not redistribute our photoassimilates in this case, and our water deficits do not help. Abscisic acid application may assist with hastening berry dehydration, but does not solve or cure the problem because the ripening signal is still missing. You have the lack of sugar stimulus in this case. So dehydrating the berries with abscisic acid application is not going to work. So I think I'm running short on time. So I'd like to acknowledge USDA and NIFA for providing funding to keep these trials going. UC Agriculture and Natural Resources, my department for allowing us the use of these vineyards. I had a lot of people work on this trial so far. Nazareth, Cliff, Lauren, and Chris have been working on these trials. And I think that is where I'm going to stop. How am I doing on time, Cindy?
You just finished with no time for questions, actually.
Okay, good.
We're ready for the next presentation. But if you do have some questions, if you click the Q&A at the bottom of your screen, there's 5 questions in the Q&A section if you'd like to answer those.
Okay.
Thank you so much for your presentation today.